We're continuing with example problems from the Taylor and Maclaurin series section. In each example problem video, we're increasing the complexity, the difficulty of the problems for each video. In the previous video, we found the Maclaurin series of different functions. In this video, we're going to find Taylor series of functions. Now remember, Maclaurin series is a Taylor series. It's just a Taylor series centered at 0. So what we're doing here is finding Taylor series of functions centered at something other than 0. Okay, and then just like in the previous video, we're not going to be proving that the function is equal to the Taylor series. We're just going to be finding its Taylor series representation. And then also find the corresponding radius of convergence. Okay, so this first problem is interesting. This is a polynomial, so we want to find the Taylor series representation for this polynomial, for a polynomial centered at 2. Now, in the binomial series section, we talked about the idea of finding a Taylor series representation of a polynomial, and what ends up happening is the series is finite. It's not an infinite series. And the reason why you can think about it is because a power series is a polynomial. So what you end up getting is the power series is the polynomial itself, assuming you show that they're equal. But I believe we might not even have to prove that these are equal. I need to look into that, but but most of the time the Taylor series representation of a function is going to be equal to the function. And so what we get is the power series polynomial is equal to the polynomial itself for any polynomial. Okay, so let's take a look at this. All right, so when it comes to Taylor series as opposed to Maclaurin series, the steps are still the same. We start by, we're going to make 2 columns, and we're going to put the function in one column, on the left column, and take a few derivatives. And remember, the function over here, we're not putting like f of x minus 2 or anything. This is the same process. This has nothing to do with the center point here, right? So if we found like e to the x centered at 0, the Maclaurin series, we get a power series. If we found the Maclaurin series for or the Taylor series for e to the x centered at 2, it would still just be e to the x is equal to something, right? The e to the x doesn't change, okay? And then even for the process of determining the c sub n, taking the derivatives, you don't have to incorporate the center point. You take the derivatives just of f of x, and then you plug the center point into the derivatives. Okay, so f prime of x is 5x to the 4th plus 6x squared plus 1. So 20x cubed plus, okay. All right, and you can see what's going to happen is the derivatives become 0. Now, what you can think about though is like technically it's still it's going to end up being an infinite series. You're adding 0 an infinite number of times. It's not like you can't evaluate the 12th c. Like you can get c sub 50 here is going to be 0, right? So it's like it's still technically the infinite series doesn't break with a polynomial. It just ends up going to 0. So it becomes finite. We're going to have 6 terms. Okay, so let's see. F of 0, 2 to the 5th is 32, plus 2 cubed is 8. So 42, then it's 50. F, okay, 2 to the 4th is 16. 16 times 5. 16 times 5 is 80. Okay, 6 times 4 is 24. Okay, 104, 105. All right. So 2 cubed is 8. 8 times 20 is 160. plus 24. Okay. 2 squared is 4. 60 times 4 is 240. Okay. Okay, so usually what we would do next is we would look for a pattern, but there's no pattern here. It's just going to be these 6 terms. So, all right. So we've got okay, so now let's go ahead and get each coefficient. So this is going to be 50 divided by 0 factorial. So 50, 0 factorial is 1. 105 divided by 1 factorial is 105. 184 divided by 2 factorial is 92. Okay, 252 divided by 3 factorial is 42. So 240 divided by 4 factorial. So yeah, remember we're doing, it's the C sub n is the nth derivative evaluated here. It's going to be at 2 divided by n factorial. This is the nth derivatives. And so we're dividing by, this is 0 factorial, 1 factorial, 2 factorial, etc. Okay, 4 times 3 is 12. 12 times 2 is 24. 240 divided by 24 is 10. Okay, 120 divided by 5 factorial. So 60. Okay. So again, we're not looking for any pattern or anything. This is it. So okay. F of x is equal to x to the 5th plus 2x cubed plus x. It's Taylor series. We're not going to put equals, but it might be the case that these are automatically equal. If you're finding that, you might not have to prove it. I need to look into that. But so okay, it's Taylor series. When you don't put with the Taylor series like this, we don't put x minus 2 here. You know, it's like it's the same idea that we don't put the function with x minus 2 in it. Same thing with the Taylor series symbol for no matter what you're centered at. It's this function of x. This is f of x. This is t of x. If you figure out they're equal, then you've got f of x is equal to t of x. It's just a function of x. Okay. And that might be confusing, but like if you found e to the x is equal to t of x centered at 2 or 0 or whatever, then like this is the Taylor series centered at 0, the Maclaurin series. This is e to the x, the Taylor series centered at 2. Well, look, everything's the same, right? Isn't that doesn't make sense, does it? Yeah, it does. The infinite series are all equal. Like if you could for any Taylor series, if you could plug in an infinite number of values and the radius of convergence was all real numbers, then you would just use the Maclaurin series every time and just plug in as if you were way away from the center. So what? Just put in more terms. You use a Taylor series centered at another point, so you don't have to use as many terms to do the sum. So, okay, this is the first term is just 50 is a constant, and then 105 x minus 2 to the first plus 92 x minus 2 squared plus 42 x minus 2 cubed plus 10 x minus 2 to the fourth, and then plus x minus 2 to the fifth. And that's it. And then now the radius of convergence, this is a polynomial. Okay, now, so I said, it's probably the case that these are equal, and it might be the case that you don't even have to prove it, but they're not equal. What is this? Well, yeah, so if the idea is if they end up being equal, which they probably are, then you could simplify this, expand all this out, and you'd get this, right? And I want to say when you do the Maclaurin series, it actually ends up coming out to be exactly this. I might be wrong about that. Like you end up getting a 3-term polynomial. This is centered at 0, right? X minus 0 with first coefficient 1. Maybe that might not be right. I'm not sure. I need to check on that. Okay. Let's do natural log of x centered at 2. So first step, we want to write the function and its derivatives. So, okay. And we've got, so, okay, this is going to be minus x to the minus 1 minus 2. So that's minus 1 over x squared. And you just want to do as many derivatives as you need in order to see a pattern. Okay. And remember, the derivatives here have nothing to do with the center point. You're just taking derivatives of the function. Okay, so minus 6x okay, let's go one more. So, okay. Now we come to this column over here and plug in the center point. So we've got natural log of 2. One over 2 minus 1 over 4 2 over 8, which is 1 over 4. Okay. This is divided by 2 is 3. So 3/8. Okay, 2 to the 5th is 32. So 24 divided by 2 is 12. 32 divided by 2 is 16. 16 divided by 4 is 4. 12 divided by 4 is 3. So 3/4. I guess we could, let's go one more. Just to make sure we can see a pattern. So, okay. 24 times 5, 120. So minus 120x to the minus 6. So okay, so let's see. 2 times 2 is 4. 2 times 2 is 4. Okay. 120 divided by 2 is 60. 60 divided by 4 is 15. So minus 15/4. Okay, so the next step is you take a glance at this and see if there's an obvious pattern. And if there is, then you go ahead and get the n formula for that and plug it in. Plug it in into the numerator here. But now, since we don't see an obvious pattern, we could potentially work on it and try and figure out the pattern. But since we don't see an obvious one, what we're going to do is we're going to go ahead and divide each of these by n factorial and see if that reveals a more obvious pattern. Okay, so we've got okay, so now for each of these, let's divide by n factorial. So we've got natural log of 2. This is the 0th derivative. That means the function itself. So 0 factorial, that's just natural log of 2. And you can see that this is not going to be a part of the pattern, so but we can pull it out of the sum. Okay, so here we've got 1/2 divided by 1 factorial. Okay, minus 1/4 divided by 2 factorial. So that's minus 1/8. 1/4 divided by 3 factorial. Okay, 3/8 divided by 4 factorial. So this is going to be 3/8 times so it's 1/64, which is 1/8 times 8. Okay, 3/4 divided by 5 factorial, so 3/4 times 5 times 4 times 3 times 2, so 5 times 4 is 20, 20 times 2 is 40, 40 times 4 is 160. Okay, and I feel like I'm missing a minus sign in here. Let's see. This is natural log of 2, then this is positive, this is negative, then this is positive, this should be negative, right? Yeah, minus 3/8. Okay, so this should be negative. There we go. Okay, so now we've got minus 15/4 divided by 6 factorial times 6 times 5 times 4 times 3 times 2. So, okay. 4 times 2 is 8. 8 times 6 is 48. 48 times 4, 16 times 3. So 482 minus 1/482. Okay. So now here can we see a pattern? And we're going to forget, we're not going to factor this in. We'll bring this out of the sum. So can we see a pattern here? Okay, well, obviously the numerator is going to be just like minus 1 to the n, or n plus 1, but the denominator. So, okay, we've got 2 to the first, 2 cubed, and then is this 2 to the 5th? No. Okay, so 2 to the 5th is 32. Okay, do we have this right? So 3/8 divided by 4 factorial. 8 times 4 is 32. 32 times 2 is 64. Okay, that's right. Okay, we could do this. If we did, so n times 2 to the n, that's 1 times 2 to the first is 2. 2 times 2 squared is 8. Yeah, okay, then 3 times 2 cubed, 8 times 3 is 24. And then 4 times 2 to the 4th, 16 times 4 is 64. Okay, so C sub n is, for the numerator, it's going to be minus 1 to the, and we're going to start at n is equal to 1. We'll start the sum at n is equal to 1, so this is going to be n minus 1. Okay, and then over n times 2 to the n. Okay, so let's actually bring this over here. So, okay, now the Taylor series is of natural log of x centered at 2. We're going to do this. We're going to say this is equal to, not equal to, but it's the natural log of 2 plus the sum from n is equal to 1 to infinity of okay, there's c sub n, but now we do x minus 2 to the n, just to the n. We didn't omit any terms or anything, just to the n. You know, you only have to change the n exponent for the x power is potentially if you have terms that are omitted. There is a term omitted here, but we taken that out of the start point. Okay, so now let's find the radius of convergence, and remember with power series, you do that. The majority of the time, you can use the ratio test to get the radius of convergence because that's just the way that the form is. The power series has the same form, right? Every power series, and it sets up well for the ratio test. But if the ratio test doesn't work, you could use the root test or potentially go to another test if you need. But the ratio test should work most of the time. So the minus 1 to the n minus 1 goes away. We've got x minus 2 to the n plus 1, so we'll put that as x minus 2 to the n times x minus 2, and then n plus 1, and then 2 to the n times 2 is 2 to the n plus 1. Okay, then we've got n, all right, and then x minus 2 to the n. Okay. So we've got okay, we can take out the n over 2 times n plus 1. This is always positive. Take that out the absolute value. So, okay, we've got the limit as n approaches infinity. Okay, we can see this is going to go to 1/2. So, and then nothing happens with the x minus 2. There's no n there. So we've got this is equal to 1/2. Okay, now this needs to be less than 1. So, okay, this absolute value inequality means, right, absolute value inequality. So add 2 to both sides. We get, and so there you go. The radius of convergence is 2 because it's centered at 2. So this makes sense. The valid inputs of x are anywhere from 0 to 4. So r is equal to 2. Okay, let's do e to the 2x centered at 3. Okay, we're going to write out the derivatives. So f prime of x is, so this is going to be 2e to the 2x. Then 4e to the 2x. So we're just going to get an extra factor of 2 out front. Okay, now let's plug in the center point. So e to the 6 to e to the 6 for e to the 6. Okay, so next what we do is we take a glance at this and see if just first glance we can see a pattern, and it looks like we can, like a simple pattern. So, this is going to be nth derivative at 3 over n factorial. Can we go ahead and get a formula for n? So we can come up with a formula for the nth derivative at 3. And we see that's going to be, so starting at n is equal to 0, okay, it's going to be e to the 6 every time. And then the coefficient out front is going to be, looks like 2n. N is equal to, no. Okay, let's see. Because when n is equal, no, that's not right. Oh, maybe it would be 2 to the n, no. So it would be 2 times n minus 1, maybe? Or no, 2 to the n, yeah. Because you keep multiplying a factor of 2 every time. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. Oh, wait. Yeah, and this was not right here. This should have been an 8. So this would be 16. So yeah, there we go. 2 to the n times e to the 6th. So there we go. We just substitute this in here, and we get c sub n and there's the c sub n. So if you can see a pattern just at first glance here, then just go ahead and plug that right in. But if a pattern is not apparent, then go ahead and apply the dividing by n factorial and see if a pattern comes out of that. Okay, so we've got so 2 to the n e to the 6th, then x minus 3, and we just put to the n. We didn't have any 0 terms or anything, so we just put to the n. Okay, now let's get the radius of convergence. So we've got the absolute value. So, okay, 2 to the n plus 1, 2 to the n times 2, n plus 1 factorial. We can write like that. Oh, and then we've also got the x minus 3 to the n plus 1. That's going to be x minus 3 to the n. Okay. Then we've got 2 to the n e to the 6. Okay. So we've got okay. So we can take out the, this is always positive. Okay. This goes to 0, so this is 0 for all x. So this is always less than 1, so r is equal to infinity. Okay, let's do sine x centered at pi. Okay. cosine x okay. Okay, now plug in pi. So sine of pi is 0. Cosine of pi is -1. So minus cosine of pi is 1. Okay, so we can see the pattern there, but we've got these 0 terms. So let's divide in factorial. So, okay, well, we start at -1, and then we alternate, we go every odd in. So we've got etc. Okay, so we've got -1 over, and then here's n, so 1 factorial is -1. Here we've got 1 over, well, we can just write the factorial. So, okay, 1 over 3 factorial. Well, wait. -1, 1, -1. There we go. Like that. So, okay. So now we can see the pattern clearly. So the C sub n is going to be -1 to the, we're starting odd, or no, we're starting with a negative, where we start at n is equal to 0. So that means we're going to do n plus 1. So when n is equal to 0, you get -1 to the 1. When n is equal to 1, you get -1 squared. Okay, now in the denominator, we're going to have, should be 2n plus 1 factorial. Let's see, n is equal to 0, you got 1 factorial. N is equal to 1, you've got 3 factorial. N is equal to 2, you've got 5 factorial. There we go. So we've got f of x, and it's Taylor series. So, okay, we're also going to need to, since we have missing terms, we're going to have to put the correct power on this. So x minus pi to the, right, because it's the first and the third. So it's going to be, let's see, yeah, the 2n plus 1, right? We're skipping x to the second, x to the fourth, etc. Okay. So now let's get the radius of convergence. Okay, the -1 of the n plus 1 goes away, and we've got, so 2 times n plus 1 plus 1, 2n plus 2 plus 1. Okay, so x minus pi to the 2n plus 3. So we've got, it's x minus pi to the 2n, x minus pi cubed, and then 2n plus 3 factorial. We're going to go ahead and do this. So 2n plus 3, 2n plus 2, 2n plus 1 factorial. Okay, then we've got 2n plus 1 factorial, and then x minus pi to the 2n. Oh, no, that's not right. X minus pi to the 2n plus 1. So x minus pi to the 2n, x minus pi to the first. There we go. Okay, so 2n plus 3. Okay. We can take out actually all of this. Not, with the squared here, all of this will be positive. It's always positive. So, okay, the limit as n goes to infinity of this is going to be 0 for all x. Okay, so r is equal to infinity.